Okay, welcome to Learning Target 5. This is probabilities involving combinations. This is probably the biggest learning target of this unit because we've done a lot of permutations even in the past unit, and so this is the biggest thing that's kind of new. And it's not that it's new, it's still combinations, but we're going to see some new strategies just using combinations that we can look at. Okay, so warm-up question, and you can take time to pause this and think about it. A task force is chosen out of 6 people. The task force could have at least 1 person on it. It could have all the way up to 6. How many ways can this be done? And so we think about okay, we can take 1 person, and so you can imagine there's how many ways there are to do that, but you can have all the way up to 6. And kind of a sub-question for that is, and it's something we're going to talk about today, is how does the 6th row in Pascal's Triangle help to solve this question? So you can think about that. And so you take time and you can do it the long way. You can see that there's 6 ways to get 1 person, but then 2 ways, if you want to get 2 people, you can say, well, it's these 2 people, then it's these 2 people, and so you got to think about all those cases. Okay, so you can try that question and then draw out the 6th row of Pascal's Triangle to see if that does that do anything. This kind of follows up on the previous lesson in the practice. So learning target today is, I know the same rules apply when solving probability problems with counting as with regular probability. You need the total number of outcomes, N of S, and the desired outcomes, N of A, which can be found using the fundamental counting principle and the rule of sum. This is not a learning target specific to this. I just wanted to write that out a little bit longer, just in a little bit of a review. And so it's kind of nice to just look at these definitions again and talk about them. But really, it's the same rules that apply with regular probability apply with this probability. And the second part of it is the sum of the rows in Pascal's Triangle, and that's why I mentioned those rows, is a helpful way of determining the total number of ways a different number of objects can be chosen from a total amount. So that's kind of wordy, but what it's saying by a different number of objects, that's what we're saying in the warm-up, where it's you've got 1 object or 2 objects or 3 objects. And so Pascal's Triangle does help out with that. So this is Pascal's Triangle. Remember, you can always draw this yourself, it's just 1, 1, 1, and then we just really add up the two above it. The outside row is always 1, so the outside number is always 1, and then the 2 numbers above each number get you Pascal's Triangle. So 2, 1 equals 3, 3 plus 1 equals 4, 3 plus 3 equals 6. So it's generally really quick to write 1, 6, 15, 20, 15, 6, 1. You may have noticed, and so this was from the question from the practice, and then if you're working on that warm-up question, you may have noticed this. 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1 is 1, 4 choose 0 is 1, 4 choose 1 is 4. There's 4 ways to pick 1 person from 4. 4 choose 2 is 6. There's 6 ways to pick 2 people from 4. 2 groups of 6 groups of 2 from 4. 4 choose 3 is 4. 4 choose 4 is 1. And so these become really very closely related to combinations. Some of the rows in Pascal's Triangle might be helpful, and you can imagine from the warm-up to add up an entire row. And so if we actually take some time to look at you're actually going to have some questions where you might actually have to write an entire row. And so there may be an easier way than just to evaluate every one of those combinations. So there's a lot of patterns in Pascal's Triangle. We did them in grade 11, and so it's useful to actually go back. If you add the rows in the triangle, you actually start to notice row 0 is 1, row 1 is 2, row 2 is 4, row 3 is 8, row 4 is 16, and row 5 is 32. And so you ask yourself, like, what's the pattern here? And so a lot of people say, well, they're even numbers, or they're doubling. Like, a lot of people can recognize they're doubling. But if you didn't have, like, the rows before, you can actually say something. These are just your powers of 2. The sum of row n, so, like, we call this actually row 5, the one with the 5 in it, because the top row is actually row 1. So the sum of any row is equal to 2 to the n. So it's actually, not only is it a power of 2, but it's the most convenient, nicest power of 2 as well. Like, this is the 5th power of 2, is the 5th row. So we'll see how that's actually used. Pascal's Pizza Party. This is a tough one. Like, I got braces like a year ago, and for me to read this question, I got them in August, and to read the question in September was very, very hard for me. Pascal and his pals have returned home from their soccer finals and want to order a pizza. They are looking at the brochure from Pizza Pizzazz, but they cannot agree on what topping or toppings to choose for their pizza. Pascal reminds them there are only 8 different toppings to choose from. And so you've got, like, pepperoni, extra cheese, sausage, mushroom, green peppers, onions, tomatoes, pineapple. Yeah, I guess that's only. How many different pizzas could there be? And so that's really the question. How many different pizzas are there? But then there's just some examples here of different kinds of pizza. Descartes suggested a plain pizza with no toppings. Okay, that's interesting. So you're counting the one where there's no topping. So that's an important knowledge. Poisson wanted a pizza with all 8. Okay, so you can get all 8. Fermat says, what about a pizza with extra cheese, mushrooms, and pepperoni? It's another example. But just to show you, like, that there's another example. And so we've got to decide how many different ways can we do this. And so we actually see, like, n of s, we'll just call it, like, the total number possible, is 8 choose 0. So we choose, like, take the 8 toppings, we choose 0 of them. 8 choose 1, 8 choose 2, 8 choose 3, all the way up to 8 choose 8. So now it's very tedious to actually, like, write all those numbers in. Like, you might get this is 1, this is 8, but then you start to get stuck on these. You gotta go to the calculator, these ones, and then maybe you get this is 8 and this is 1 again. It does, like, take that Pascal's triangle where it goes up to a highest number and then goes back down and repeats itself. So you don't ever have to evaluate all of them, but there is that quicker way. It's the 8th row of Pascal's triangle. Since the row in Pascal's triangle add up to the power of 2, you actually have 2 to the 8, which is 256. So this is a very interesting question. Is a very interesting way to do it. This is not to do with Pascal's triangle. This is just like a combination question. ODSS art auction has 5 sculptures. ODSS is 5 sculptures, 3 pieces of modern art, and 2 charcoal sketches. Miss Petra wants to pick 3 works to make a display. How many ways can she pick 3 pieces that include some modern art? This word "some" like comes up before as well, and maybe wouldn't use it on a test, but the word "some" says you have to have at least 1 piece of modern art. So N of A, the first solution we can do is actually, like, break it up into cases. So case 1 is, like, you got 1 piece of modern art and 2 other pieces. And so to do that, you got 3 choose 1 and 7 choose 2. So 3 choose 1 is the 3 pieces of modern art. You're going to choose 1 of them, and is the multiplication sign. Out of the 7 remaining, we're going to choose 2 of them. You don't want to, like, break up the 5 and the 2. If you start to, like, if you don't do the remainder, if you start to do the 5 and the 2, it becomes very hard to get all the cases. That's 3 times 21, which is 63. Case 2 is where you have 2 pieces of modern art and 1 other piece. So you got 3 choose 2 and times 7 choose 1. Looks very similar. You're just changing the numbers. And that's 3 times 7, which is 21. And case 3 is where you have 3 pieces of modern art and no other pieces. That's 3 choose 3 times 7 choose 0. Even though you don't have to write 7 choose 0 because it's just 1, you don't even have to write 3 choose 3 because it's just 1. It's helpful to write both of these so we can see the link between the other cases. So it's 1 times 1, which is 1. And so n of a equals 85 after you add them up. And so this is your rule of sum, you add them up. Rule of sum to me almost becomes common sense, where you've got these cases, you've got 63 ways to do it this way, 21 ways to do it this way, 1 way to do it this way. It only makes sense to add them up. But I can see how you would add these here, because it becomes tough. But remember that these here are kind of like in algebra with terms. The multiplication connects the term together. And so that's another way to think about and. You can also work with the slot method as well. Solution 2, like you can imagine, well, there's that indirect method too, where you just subtract the case where you have no modern art. N of S is the total ways to pick any art. That's something you need to know. You probably need to know that for probability anyway. But like, it's good to, if you get that, the total ways to pick any art is 10 choose 3. Out of the 10 pieces of modern art, you got 3 of them to choose from. A prime is the number of ways to pick no modern art, and so if we take 120, no modern art is 7 choose 3. I left off the 3 choose 0, but I'm kind of regretting that. So it would, like, you probably should write 3 choose 0 times 7 choose 3, but you don't need it. And then n of a is 120 minus 35, give you the exact same answer. Just to show you, like, the indirect method is quicker, but sometimes you have to do cases anyway, so it's nice to see both ways. Probability for lottery, so you just put lotto 649. Here are the rules here. It's very straightforward. You pay your money, you can get either random or you can pick your 6 numbers. Your 6 numbers have to be between 1 and 49, so that's why they call it 49, and they call it 6 because you're picking 6 numbers. Probability of winning the jackpot. We've got like probabilities over here, and so we just included this so that you could see what they're saying. Notice how they say odds of winning, and that's definitely not odds; it's a probability. Again, in like just layman's terms in daily life, often we say probability not as probability but odds. People are just more comfortable with that word odds, even though those are not odds. So probability of winning the jackpot. So n of s is actually 49 choose 6. Order doesn't matter in the lottery, so you don't have to match them in the correct order. You just have to have the 6 numbers. So the number of ways to do that is to, like, the number of what numbers that are out there are 49 choose 6. It's 13,983,816. N of a is 6 choose 6, and there's actually unwritten here, just like before, there's that remainder 43 choose 0. There's 43 losing numbers, and we're choosing 0 of them. So by the way, it's 1. There's only one way to win the lottery. You got to get all 6 numbers. So that's where you kind of see the probability as 1 out of 13,983,000. That's exactly what they say on the website. So they're not lying to us. I'm matching 4 to 6 numbers. So again, we've got n of s is 49 choose 6. N of a, you got 6 choose 4. So out of the 6 matching numbers, we're going to choose 4 of them. And out of the 43 non-matching numbers, we're going to choose 2 of them. When we multiply that together, we get 13,000. And the probability of that is 13,000 out of 13 million, which is 0.0969%. So just under like under 0.1%. Very low probability still. Remember that's percentage. It's when you actually divide these numbers, you get 0.000969. And I just want to show you there that when you look up at the matching 4 to 6, you get 1 out of 1033. If you divide those, you get the exact same thing. Okay? And so there's your practice for today.